Hello everybody, this is Dr. Pennington again, and in this video I'd like to talk to you about balancing redox reactions, both under acidic and basic conditions. We'll talk about what that means here in just a minute. One quick thing about redox. If I was to ask you the question about what do you understand by the term redox, I'm hoping you'd understand that redox is made up of two parts. Red for reduction, and oxidation. If you remember the basic mnemonic oil rig, oxidation is loss, reduction is gain. That's a really useful thing to remember, and we're talking about gain and loss of electrons here, and that's exactly what we're dealing with in this case. So one thing you might be wondering is, well, why on earth are you having a whole video about balancing reactions? We've done that before. I thought that was simple. Well, yes, what we have done before is simple, but if I was to give you a couple minutes and just try to balance this, well, let's see what would happen. Okay, one manganese. I've got oxygen all over the place. I'm going to leave that till the end. Carbon, one carbon, two carbons. I'll put that there. So I'll balance my carbons, I balance my manganese. I got 4 oxygens, 8 oxygens, 6, 8 oxygens. Cool, I'm balanced. Oh, no, I'm not balanced, am I? I haven't balanced my charges. That is the one thing that is going to make redox reactions a pain in the butt. At least if you try to balance this way. Because not only do you have to balance the number of atoms of each species, but you've got to balance the charges as well. And that's not something we've had to worry about too much before. It's just sort of always happened. So just think about it. -1, -2, giving a total negative charge of -3. 0 for this, -2, but 2 of those are -4. -4 here, -3 here. And I can guarantee you, whatever manipulation you try to do with these 4 species, you will not get to the answer. But I'm going to take you through how to get to the answer. Alright? Balancing redox reactions is all about following a set of steps. Alright? Making sure you follow these steps and follow them in order. Alright? So let me just go through what those steps are. Step 1. We want to take our overall reaction and split it into 2 so-called half reactions. A half reaction is literally where you take the reaction and split it in half. You're going to take the species that look most similar and put them together in a half reaction. So MnO4- goes with MnO2, just as C2O4-2- goes with CO3-2-. So let's go ahead and do that. So MnO4-, we're going to leave the states here as well, goes to MnO2 solid. Now, of course, that's not the overall reaction. That's not balanced. All right, but we're going to do some balancing here in just a minute. And then when we go down here, we've got C2O4-2-. Again, not forgetting the states, goes to CO3-2-, and that's aqueous as well. Alright, now I'm just going to erase this. It doesn't mean that we're forgetting about it. I'm just making myself some room. So at this point, we're just trying to come up with our half reactions, and that's what we've done. So step 1 is done. We've done our half reactions. Step 2 tells us that we're going to balance every atom, or we're going to balance atoms other than oxygen and hydrogen in each half reaction. Now, other than oxygen and hydrogen, well, there's no hydrogen here yet, but those will be manganese and carbon. So when we look at the top reaction, 1 manganese on the left, 1 on the right, so we're okay there. 2 carbons, 1 carbon, so we've got to balance those. So step 2 is done. We have now balanced for atoms other than carbon or hydrogen. And the real meat of this comes into play when we do balance oxygen and hydrogen. And we're going to balance oxygen first. And we balance oxygen by placing water molecules, as odd as it sounds. On the side that is lacking oxygen atoms, or the side that has less, we add water molecules to make up the difference. Alright, so when we look at our first half reaction, We've got 4 oxygens here, 2 here. So that means that we need 2 water molecules. Alright, and these are just standard state water molecules, so just liquid is fine. And when we go over to the other side, notice we have 6 oxygens here. It's not 3, it's 6, and we've got 4 here. So we're going to put 2 water molecules here as well. So we've balanced our oxygen. Now we're going to go on to step 4, where we balance our hydrogen. And for that, we're going to use H+ ions. Alright. Now notice, in most cases, the only place the H+ ions come from, or the only reason they're needed, is because you added in hydrogens from the H2O, but that's okay. So we do exactly the same as we did for oxygen. We put the hydrogens on the side that they are needed. 4 hydrogens on the right for the first half reaction, 0 on the left. So therefore we need some H+ on the left hand side. But how many do we need? Well, we need a number equal to the hydrogens on the other side. So that's 4 here. So therefore we need 4 hydrogens here, 4 H+. Alright. Now let's go down to the other reaction. 4 hydrogens again, 0 here. So therefore, so. Alright. Now one thing to check at this point, it's always a good thing to make sure that you're doing this right. If you're balancing your reactions and you're finding that the H+ are on the same side in each case, make sure to check your work, because that probably means that you've messed up somewhere. Not always, but probably. Alright. Okay, let's move on to the next step. Now we've balanced the hydrogens as well. Now we're going to balance the charges, and for that we're going to use electrons. Alright. Now this is where we have to be very careful, because it's really easy at this point to get messed up. We have to make sure we look at the charges on both sides of the equation and carefully add them all up. So when we look at the first half reaction, there is 0 overall charge here because there's no charges. The charge here is -1, +1, but oh, sorry, there's 4 of those, so that's actually +4, -1, giving a total of +3. So that overall charge is 0. That overall charge is +3. Now bear in mind, we are only balancing the charge by placing electrons. Electrons have a negative charge, so if I was to put electrons on this side, I'd have minus and plus. Those charges wouldn't be balanced. I want both my charges to be the same. So therefore I will always put my electrons on the side that's got a higher positive charge, because adding the electrons will work to bring that charge down. So if we have a charge of +3 and here we've got a charge of 0, how many electrons do you think we need to add on this side? Well, of course that would be 3. 3 electrons. Don't need to worry about a state for the electron. Now when we go down to the bottom, total charge here of 2- from here. Total charge here of 4+, 2-, oh no, hang on, forgot about that. There's 2 of these, so that's 4-, 4+, given a total charge of, well, apparently 0. Now, we're going to apply exactly the same rule that we did up here. We said that because the electrons are negatively charged, we put the electrons on the side that has the highest positive charge. Well, neither of these have a positive charge, but 0 is more positive than 2-. Plus, the only way to cancel out 2- is to add 2- on this side. So it really comes down to algebra. So that means we add 2 electrons on this side. Alright, so we are moving right along. This is looking good. Now, one thing about redox reactions that I haven't mentioned yet, but it's actually really important. The only way a redox reaction is going to work is if you have an equal number of electrons lost and gained, which means we have to equalize the number of electrons in one reaction with the number of electrons in the other. Alright. Now let's, just before we do this, I want to see if you guys can actually understand which reaction is which. One of these is oxidation, one of these is reduction. If you remember, oxidation is loss, reduction is gain. You are looking at what's happening to the species on the left, the starting materials. Are the starting materials gaining electrons or are they losing electrons? Well, when we go from here to here, notice some reaction has occurred and these electrons have now been spit out. Those have been lost from here. Nothing's been lost here. In fact, the electrons are being added in, so those have been gained, which means that this is our reduction and this is our oxidation. So in reduction, the electrons will always be on the reactant side, the left-hand side. And in oxidation, the electrons will always be on the products, or the right-hand side. And another way to check at this point is if you have electrons on the same side in each equation, that's a guarantee that you've messed it up somewhere. And that's not even a possibility. It's absolutely true. You've messed up somewhere. Alright, so let's get back to where we were. 2 electrons, 3 electrons. Obviously 3 is not 2. So how do we make this equal? Well, we look for the lowest common denominator, and of course that's 6. So therefore we're going to multiply this by 2, but of course that means we multiply the whole equation by 2, and it also means we multiply this whole equation by 3. Alright? Now of course that means a good bit of writing here, but let's see what we can do. So when we do the first half reaction, 6 electrons and 8H plus, I'm going to write kind of small here so I can make sure I fit everything on one line, plus 2 MnO4 minus. Alright, and that goes to 2 MnO2 solid and 4 H2O. Alright, so that's our reduction half reaction done. So let's do the same for our oxidation half reaction. 6 H2O, liquid again, plus 2, that should be 3 C2O4 2 minus, and that forms 6 carbonate, 6 CO3 2 minus, plus 12, we're going to get some big numbers occasionally, 12 H plus aqueous, plus how many electrons? 6 electrons. Alright, okay. Now, all we got to do at this point is just cancel out and add together. So the first thing we can cancel out are the electrons, and that's fine. We know this is a valid redox reaction because we've lost the amount of electrons that we've gained. But notice for other species we have things on opposite sides that are the same. We can cancel out 4 waters on each side and get left with 2 here. We can cancel out H pluses on each side and get left with 4 here. Everything else is an individual species, so we are done as far as that goes. So I'm just going to write out the overall reaction. 2 MnO4 minus aqueous plus 3 C2O4 2 minus aqueous plus 2 H2O goes to 6 CO3 2 minus plus 4 H plus. Now just check. 4 hydrogens, 4 hydrogens, 6 carbons, 6 carbons, 2 manganese, oh I forgot the manganese, hang on, plus 2 Mn, that's kind of important not to forget stuff. So 2 manganese, 2 manganese. Now oxygens, 8, that's 12, so that's 20, that's 22. That's 18, that's 4, that's 22. Alright, so all our atoms balance. Now for our charges, 4 plus, that's 12 minus, that gives 8 plus. No, I'm sorry. 4 plus 12 minus, that gives 8 minus, I'm sorry. And that gives 6 minus, 2 minus, 8 minus on each side. Alright, so that means we are balanced. Now, is there any chance at all that you could have tried to balance this using a normal method and come up with this? Well, of course not. That's why redox reactions are a little bit more involved. Now, before we move on, I just want everybody to see. Notice one of the species here in this balanced equation is H+, which means this implies this reaction has been run under acidic conditions. But what if that reaction was to be run under basic conditions? All right. Now it turns out to balance a redox reaction under basic conditions, it's exactly the same as under acidic conditions, but you've got a couple of extra steps to add in. And I'm going to write these in green just so you can differentiate them. All right. In fact, I'll tell you what. Let me do. Let's see. I will just do that here, just so you can understand that the green is for the basic here. All right. In fact, it's probably a good idea if I just get rid of that too. So that's under acidic conditions. When we are trying to balance something under basic conditions, a couple of extra steps. We need to add OH minus ions. So we add OH minus ions. We add them onto, or we add enough OH minus ions to neutralize all the H plus. But the thing that's different about adding OH minus ions is that we add up to both sides of the equation. All right. And we'll actually go through this on the next slide. In fact, we can probably just do it here. We can just do it here just to save going on to another page. We add OH minus ions. Now, what do you think happens when you add H plus and OH minus? Well, of course, you get water. All right, so on one of these sides, the sides that has H plus ions, you are going to add OH minus. I'm sorry, you're adding OH minus on both sides. On one of the sides, you're going to form a bunch of water molecules. All right. And then once you've done that, cancel out as needed, because you form new water molecules that might give you the chance to cancel some other things out. Alright, so the question becomes, if we've gone up to step 5, which we have, for step 6, if we wanted to balance this in terms of basic solution instead, we go all through the 5 acidic steps and then go to step 6. Add OH minus to each side. So how many OH minuses on each side? Well, to neutralize this, we need 4. So I'm going to write that, 4 OH minus on each side. Now, what's going to happen when I add 4 OH minuses here? What am I going to form? All right, if I add 4 OH minus here, what am I going to form when those two react? Well, of course, they're going to form waters. Now, how many waters are we going to form? Well, we're going to form 4. So in other words, I'm just deleting the OH minus and the H plus. I can do that on here. Obviously, you guys can't do that. At least not when you're writing in pencil, but you can see where we're going here. So it's a little bit more erasing for you guys to do. It says form H2O. Well, we just did that there. Notice the OH minus ions left here. We didn't do anything with, and we can't do anything with because there's no H plus there. Form H2O and cancel out. Now the only thing we can cancel are water molecules, because here we formed 4 and we had 2 left. Alright. So we can cancel out those and be left with 2. Which means the overall balanced equation here under acidic conditions becomes this. I'm just going to put the OH minus here, and I'll erase it from here. Alright. That then becomes 2. And notice one of the species left over now is OH minus. You guys know OH minus is base. Therefore, basic conditions is what we've just formed. Now let's just check everything balances. 2 manganese, 2 manganese. I mean, that shouldn't be a surprise because we haven't done anything with those. 6 carbon, 6 carbon. But the oxygens and hydrogens are going to be where it could be potentially problematic. 4 hydrogens, 4 hydrogens. Well, that's fine. 4 oxygens, 6 oxygens, 18, 24 oxygens. 12 plus 8 is 20, plus 4 is 24. Alright, so we're balanced for all our atoms. Now for our charges, just to be sure, 6 times 2, that's 12 minus 2, that's 2 minus 8 minus, that's That's 2 minus, 6 minus is 8 minus, and 4 minus is 12 minus. So everything's balanced. So therefore, that is how you balance redox reactions in acidic and basic solution. Just remember, basic is not any more complicated. It's just the same thing as acidic, but with 2 extra steps. All right, that's it. Thank you.